Hi, it's Mr. Mac, and you can see a beautiful picture of Cronulla with the waves breaking onto the rock pool, and I'm going to introduce you to wave properties. And here are the NISA outcomes for this part of the course, and I'll leave those for you to look at, but we're going to work through them bit by bit. So what is the inquiry question? Simply put, what are the properties of all waves and wave motion? And what are we learning to do? We want to describe the relationships between characteristics of different types of waves that transfer energy. And the success criteria. Well, we'll be able to solve problems and make predictions using the wave and frequency equations in a variety of situations. Well, we know what water waves are. We experience them when we go to the beach. And we can see that they are mechanical waves. They carry energy from one place to another. We know that when we're swimming and we feel the force and the impact of waves one after the other. If we looked at one point on the surface of the water, we would see it go up and down, a bit like this cat in a life buoy. And a wave is a disturbance that propagates or moves from one place that it was created to another. Actually, it's a bit more complicated than that. So you can see this seagull actually does a motion in a circle. We'll look at two different types of waves. Firstly, transverse waves, and secondly, longitudinal waves. So what are some wave characteristics? We receive waves all sorts of ways, such as sounds that are transported to our ears, light that comes to our eyes, and electromagnetic radiation to our mobile phones. Through wave motion, energy can be transferred from one source to a receiver without the transfer of matter between the 2 points. So here we see a diagram with a cross-section showing the wavelength between two crests or two troughs, and the amplitude is the height that the wave rises above its median point, its maximum disturbance. And you can see that this is a position displacement graph. The picture shows a snapshot of the waves on the surface of the water. Well, here are the two different types of waves. Can you see them in the long spring or slinky? And the first one shows a transverse wave, and the second one is a longitudinal wave. What do you notice about the difference between the disturbances as the wave or the pulse moves from left to right? You can see that the transverse wave, the pulse goes up and down. For the longitudinal wave, it seems like a compression is moving from left to right. Well, this animated GIF in the top right shows a Mexican wave, and one of my Year 12 classes, whenever I mentioned the word wave, they would instantly stand up and do a Mexican wave along the back row. And we've probably seen these at stadiums or Olympic events. In the middle there is a diagram showing a snapshot again of the main features of a set of waves. So the wavelength, the crests, the trough, the amplitude, and showing how the media vibrate in a certain direction. These are transverse waves, and it's a simple wave that consists of a periodic disturbance that propagates from one place to another. The wave in the diagram shows the crests and troughs, and the amplitude is the distance from the rest position to the point of maximum displacement. And the wavelength is the distance from one crest to the next, to put it simply. Well, on this slide, we can see, again, an animation of transverse waves. If you look very carefully at one of the red dots, you'll notice that it simply goes up and down. But it seems like the waves are moving steadily from left to right. That's the principle of passing energy from left to right, even though the matter stays in one place and vibrates. So now we turn to longitudinal waves. Longitudinal waves propagate in the same direction as the direction of the disturbance. So you can see there the diagram of the slinky. There are two compressions. and the distance between the two compressions is the wavelength. In between, that area that is a little bit more stretched is called the rarefaction. And there are three definitions that we need to learn. The wavelength is the distance between two compressions, to put it simply, and we've given that lambda. The frequency, F, is the rate per second of a vibration constituting a wave, either in the material, such as in sound waves, or in an electromagnetic field, such as in radio waves or light. The period is the interval of time, measured in seconds, between successive occurrences of the same state in an oscillatory or cyclic phenomenon, such as a mechanical vibration, an alternating current, a variable star, or an electromagnetic wave. It is simply found by the formula capital T for period equals 1 on F, inverse of frequency. And this is a great animation of longitudinal waves showing the particles vibrating backwards and forwards. And now we come to our worked example 1 about graphs. So I'll show a graph, and from the graph you need to find the period, frequency, amplitude and speed of the waves given that the wavelength is 2.0 meters. Here's the graph, and one of the skills that we need to develop is how to interpret the graph. Well, firstly, the period is 20 seconds. You can see that by a complete wavelength. As I draw, you can see it goes up, down, and then comes back to the same point in the same direction. That's one complete wave, and it takes 20 seconds just by reading it off the graph here. The frequency is 1 on that time period, so 1 on 20 waves per second. The amplitude is 15 centimeters. To find the amplitude, we find the highest point and we go to the rest position. And again, we read off the graph 15 centimeters. And the speed of the waves is given by the wavelength, 2 meters, and the frequency times the wavelength. So the frequency is 1 on 20 times 2 is 0.1 meters per second. And that's our first example. Now I'm going to give you some time to complete exercise set 1.